Right, now that we've had a very entertaining start to our lesson, we're going to actually learn a little bit about alcohols. We met alcohols last year, and we know that their functional group is looking for an OH somewhere. So you're looking basically for R being some carbon chain, OH. Because it's got the oxygen already in the formula, they burn quite well, so they undergo complete combustion quite readily. And that's one reaction we're not going to look at in much depth. What we're really going to look at first is how we classify them as primary, secondary and tertiary. Then we're going to look at the types of reactions that alcohols undergo and how we can use these reactions to work out whether we have a primary, secondary or tertiary alcohol when we're asked in a test, or if we have to do a practical on that. So the first thing is to look at how we classify them. Now I'm going to use a 4-carbon alcohol as my example. So the isomers of butane 1-ol. So we'll start with butane 1-ol, which is CH3, CH2, CH2, CH2OH. Then we'll look at 2-butanol. And we're going to look at methyl propane 2-ol. Again has 1, 2, 3, 4 carbons, so it is a structural isomer of those others as well. If we have a look at the carbon-oxygen bond, that tells us what we've got for whether it's primary, secondary or tertiary. When we look here, here and here, we look at how many carbons the carbon attached to the oxygen is bound to. In our first one, butane 1-ol or 1-butanol, there is a single carbon-carbon bond there, so we call this a primary alcohol. Here though, it's bound to 2 of them, 2 other carbons. So we're looking at the carbon, not the oxygen. So it's what we call a secondary alcohol. And here, we can see that we've got 3 bonds on that 1 carbon, so it's tertiary. The relevance of this sort of comes in when we look at the reactions. So what I'm going to do is look at types of reactions and what happens with each of these. So one of the most common things we do with alcohols is we try to oxidize them. So we can use acidified permanganate or acidified dichromate for this, and they both have the same outcome, albeit with different reduced versions of those reagents. So I'm hoping this fits on here, the MnO4 minus in the presence of an acid. We can have Cr2O7, 2 minus, in the presence of an acid. And the other thing that we often use to distinguish between these is a thing called the Lucas test, or a Lucas reagent, where we're trying to turn it into a chloroalkane. And that's anhydrous zinc chloride dissolved in concentrated hydrochloric acid. It's what we call the Lucas reagent. When we see the word reagent in there, it tends to be a giveaway that it's a test for something. So Benedict's solution or Benedict's reagent is used to look for glucose in biology, that sort of thing. So this is actually a test for types of alcohols, particularly tertiary. Right? So what we're going to see what we would observe happen, and then back that up with an equation to show us what's happening. So if I work my way across rather than downwards, so focus on each reagent, and we'll see what would happen. Permanganate itself is purple. If it reacts in acidified conditions, it turns to manganese 2, which is basically colourless. It's ever so slightly pink, but it's actually colourless for all intents and purposes. A primary alcohol will oxidize in the presence of acidified permanganate. So this will go colourless. Secondary alcohols will also give us a positive. So they will also go from purple to colourless. But tertiaries cannot. And this will become obvious shortly when I show you what the organic products are. So this one will remain purple. So why is that happening? Well, in a primary alcohol, we're able to oxidize it by removing 2 hydrogens. And what this makes is a carbon-oxygen double bond. So you end up making, in this case here, CH3, CH2, CH2, COH. And this is called butanal. It's an aldehyde because it's got this COH, or this double bond CO, I should say, at one end of the molecule. So it's what we call an aldehyde. In this case, butanal. We'll talk about aldehydes more later. Alright, at the moment we're just focusing on it as being one of the products. Now the nice thing with this, if you have enough permanganate there, then it will actually continue on to make the carboxylic acid, butanoic acid. It's got a very characteristic smell. It smells a bit like Parmesan cheese that maybe has been left out for a little too long. Or if your nose picks it up that way, it smells a little bit like you've just been sick. Alright, so you can sometimes get a characteristic smell come up. You go, right, that was butanol because it now smells very sickly. Okay, so it could go all the way to butanoic acid. That H becomes an OH, which is further oxidation. Okay. Generally, if we do this by distillation, then the butanol has got a lower boiling point than the alcohol, and so it will be collected, and it can't carry on to react to become the butanoic acid. If you do it by a thing called reflux, though, which I'll let you find out about more later, then the butanol continues to react, and that's how you make the acid. Alright? So, if we did this under distillation, sorry, different colour needed, then we would make butanol. If we did it by a process called reflux, then we'd make butanoic acid. Which is this. Basically in reflux what you're doing is heating it, and you have a condenser on top, and the condenser has cold water flowing around the outside tube of it. It cools down all the vapours, sends them back in so they can keep reacting. Okay. So I'm not too worried about going over this one because it's the same result, just different colour. Okay. With a secondary alcohol though, once I make that carbon-oxygen double bond by removing two hydrogens, this one and this one, then there's no ability for it to further oxidise. So what I'm going to end up making here is this. And as you can see, I can't put an OH or an H or anything in there without breaking a carbon-carbon bond. And oxidation is not going to break a carbon-carbon bond. Okay, it's just not going to do it. So that's the end point. This one here is called butanone. Because there's only one place that the carbon can go, because if it was here it would be a mirror image of it. Because there's only one place, I don't have to number that. So I just call it butanone. Once you get to 5 carbons, though, you have to number where the CO bond is. Alright, so once you get to 5 carbons, so pentanone would have to be numbered as 2-pentanone or 3-pentanone. Alright, but again we'll do ketones later. This you'd probably usually do by reflux, but you could actually do it by distillation, but you could of course do it by reflux because it can't react further. Okay. And of course if this stays purple, then there's no reaction. Now the reason that I've gone over the dichromate is not just a lack of planning, it's because you get the same compounds being made. So dichromate itself is orange. It goes a little bit of a yellowy colour sometimes when you acidify it, but it is orange. So in this one it is going to react. Orange, and it turns into chromium-3. And chromium-3 has a bluey-green colour. Because you tend to end up using too much dichromate, the orange of that makes it appear very green. Rather than being bluey-green, you just get a normal green. So we get that observation here. Same thing with this, because a reaction is occurring. Orange to green. And in this one, it's going to remain orange, because nothing's happening. So, using just a an oxidant, so one of these two here which are called oxidants, you can actually tell if you have a tertiary alcohol present, because the tertiary alcohol will do nothing. But you can't tell the difference between these two. That's very, very difficult to do. So what we often do to tell these two apart is use the Lucas reagent. It's actually also a very good test for tertiaries, but that's not conclusive enough. You need to back it up with oxidation as well. For some reason, which I won't get into today, this carbon-oxygen bond is harder to break than this one, which is harder to break than this one, for another what we call nucleophile, another thing that will try to be attracted to another nucleus, which this amount of chloride is providing. Okay? So what we observe is that if the reaction is successful, it makes two layers, and one of those layers is cloudy. That cloudy layer is the chloroalkane. If you just don't see anything happen, it just sort of goes a bit sort of opaque and nothing at all happens and it stays as one layer, then nothing's happened. Alright? So it's quite a viscous sort of solution, this. You can see it sort of work its way down the test tube. Alright, so if we were to say we're going to put it in warm water for up to 5 minutes, what we would observe is no reaction here. Even after 5 minutes giving it heat. In these two, you would observe two layers and one of them's cloudy. And you'd see that in both. This would actually happen almost immediately. So what we need to do is we need to actually say what's happening. We can't just leave it like that. In an assessment, we need to say what's happening. So what's happening is the chlorides in this reagent are displacing the OH. So we're making 2 chlorobutane here, and in this one we're making methyl 2-chloropropane. If you can remember those reagents, you're pretty much sorted. Now, there is another reaction you can do with these, which I haven't put up there, which is to put concentrated H2SO4 with it. Concentrated H2SO4 is a dehydrating agent. It will rip a water molecule out of these. So, for example, it would take the OH out of that and then an H out of the neighbouring, from a neighbouring carbon. So it would remove HOH, H2O, creating a double bond in here. But we already met that one briefly when we did alkenes. Right, same thing here. Give you 2 possible answers. The double bond could go there or there. And again, we looked at when we did chloroalkanes. And here, you can move OH there, and one of those other H's will give you the same product.